So we don't need these microphones. Okay, good. Okay, good afternoon. So as Nikhil said, this is joint work with Mohit Singh, who just moved to Georgia Tech, and Nishit Vishnoi, who is at EPFL. So the topic is rounding, and let me first before getting into the formal setting, let me just give you a quick example. So suppose I want, if I have a square and I have a point in the middle, I know how to write it as a combination of the vertices. Now, if I have another polytope in high dimensions, there are many options, but let's look at the parallelogram. So the one thing, again, there are many ways. What we will do following Lovett and Mecca is run a motion or discretize it to a random walk till it hits a face. And then once it hits a face, we run in that face. We run a Brownian motion in that face till it hits one of the vertices. And so by doing this process, you get the distribution on the vertices. And it turns out that this way of rounding has good properties in certain polytopes, but not in others. So it would in this parallelogram, but it wouldn't. This is our polytope. So, and the good property we'll want is that the coordinates be negatively associated or negatively dependent. I'll say more about this in a minute. So again, the basic problem that occurs multiple times is given a polytope and a point in its interior to find the distribution over the vertices, which whose average is the given point. So of course that exists, and there are usually many choices. And okay, this is the vague thing. We want that the random vertex chosen will be a lot like the interior point we started with. So what does that mean? Basically, we're looking for concentration. So if you look at nice functions of the coordinates, apply them to the vertex, we want that to be close, typically, to the same function applied to the interior point. So, and this type of problem occurs a lot in approximation algorithms. So when you do in any kind of integer programming, you relax it, you get a solution in a convex hull, and then you want to get a solution to your original problem, so you have to round. And the problem is to have a good rounding procedure. So if your interior point maximize some function, you want the rounded point to have close to the same value of that function, and then you're likely to get a good approximate solution. So, the topic of rounding is big. In fact, Mohit and co-authors have a book on it for from some years back on the other methods of rounding. Mohit and Nishit have a paper on rounding using maximum entropy distributions. Often these are good, but here we will, but they're not always guaranteed to have the negative dependence properties we would like. So remember, in the standard Chernoff bounds assume that the variables you have are independent, but the proof readily generalizes if the variables have some negative dependence, negative cylinder dependence. And stronger negative correlation gives you stronger concentration for more functions, not just the sum of the coordinates, but some of more involved functions of the coordinates. I'll say something about that in a moment. So, as I said in the example, the rounding procedure we use following Lovett and Mecca's success in discrepancy theory. So the process we'll use, given a polytope and a point, you start a random walk. So again, structurally, it's the cleanest argument is when you do a Brownian motion. Of course, algorithmically, you'll want to discretize the Brownian motion to a random walk. So you start a Brownian motion until you hit some face, and then you continue Brownian motion restricted to that face until you hit the face of lower dimension, and iterate. Each time you will hit the face of lower dimension until you must end at the vertex. And the probability you end at each vertex is our distribution mu. So because Brownian motion or the random walks we will use will always be martingales, it means that the expectation of the random node you select is indeed the initial point you started with, theta, and this survives when you use these stopping times. However, so you get a random point, and we're in some high dimensional space, so it has n coordinates, and we'd like these coordinates to be negatively dependent. That doesn't always hold. So it turns out it does hold in a big class which is widely studied, namely matroids that come from the basis, polytopes that come from a basis of a matroid. So this kind of topic has been looked at with great success for spanning trees where the maximum entropy distribution, which has a simple product form, has very strong negative correlation properties, even strong Rayleigh, so stronger than negative association. But that's a restricted class, and again so for a restricted class we have very strong forms of negative dependence, and we have weaker forms for other notions of rounding, but not the notion of negative association. So just since I didn't write the formula in the slides, so we're going to get in the end from this procedure a random vertex x, think of it as a vector, x1 to xn, and negative association means that if you take two disjoint subsets of the coordinates s and t, and then and you apply f and g, which are increasing functions, so I didn't write that down, but f and g are monotone increasing functions, then f of xs and g of xt are negatively correlated in the standard sense written here. So expectation of the product is less than the product of the expectations. So this allows you to combine a bunch of coordinates by an increasing function, which is not necessarily linear. So and still have this negative correlation. So the random walk we're going to use is not a general random walk, it's a Gaussian random walk, which is what you get if you run a Brownian motion, just sample it at discrete times. And there's a reason to that beyond that that's a discretization of Brownian motion. Namely, Gaussians have a wonderful property not shared by other distributions, that to check negative association for in a Gaussian vector, you just need to know that the coordinates are negatively correlated. So so you just have to check 2 by 2 correlations, and you get this very strong negative association property. So that's a classical result from the 70s of Jogdev et al., Barlow and Jogdev. And so this is the basis of what we use. So the proof combines that ingredient together with stopping times, and property of matroids. So the polytopes that we use is the convex hull is defined by the basis of a matroid, and the uncrossing property of matroids implies that whenever you restrict this random walk to a face, the correlation is indeed negative. So, so that, the details are in the paper, which is short. But once you have that, then you just combine this uncrossing property of matroids together with this property of Gaussians to get the negative correlation. And we don't know for which matroids you have the stronger property of strong Rayleigh. So let me end with just one open problem, which is suppose you have, so here is a related open problem. Suppose xn, x1 to xn are now just random bits which are negatively associated. So they're now just two valued, and you look at Lipschitz functions. So maybe I don't have time now to state the problem in general, so I'll just say that that the stronger form of negative dependence, which is strong Rayleigh, is known not to hold for all matroids, but it's open whether it holds for a subset of the matroids. Stop here.
Any questions? Thanks.
Yes.
How long do these procedures take?
N squared over epsilon, but maybe we'll take this offline.
Sure.